I'll be presenting a case study on unique tower which is coming up in Chennai. And the presentation overview, I'm going to talk about the basic understanding of tower and what is the engineering design that has gone into it and how it has been constructed, including the fabrication part. The understanding, this basically a 132 meter tall tower constructed for the purpose of office space and constructed for the office space. Actually, it has got a stem going up to this, that is around 90 meters. Above that, we have got a Bava, which is catering for the office space. And this is the overall site layout, and the building is located in this place. So these are the engineering buildings already been constructed of around 5 stories each. And this is the three-dimensional view, and this is the tower which is coming up, and these are the already existing engineering buildings. This is the stem portion. The office space starts at 90 meters, and over which we have got a butterfly roof truss and central spine. The application of steel happens basically at this location above 90 meter level. The structural system, these are the typical floor plans, and you can see the complete vertical systems are made up of RCC. This is a completely a stem portion is made up of RCC walls. As we go up, the walls are shrinking. These walls are reducing as we go up. You can see it here. This keep reducing, and this is the elevation wall. Actually, it's bending towards back, and it keep reducing as we go up. So this indirectly we have got an advantage. You can see it, the center of gravity here, what goes up as we go up. Since this bowel is projected towards front, we try to maintain the siege is very close to the center of the wall. So that's one of the advantages what we could derive out of the slanting wall. And this is the typical, this is the floor at 91 meter level. This is the first level which is going to support all the floors above. So we have got a central RCC core from where radially all the steel beams are projecting. So these steel beams are supporting the floors above. To give a clarity, the next page, the section is taken vertically like this. So this is how it is. So we have got a RCC central slab from which the radial beams are projecting. This being cantilevered, over which the complete column is taken and each floor being supported. Here the girder is of steel, and this complete floor systems are made up of steel with the floor being steel deck with a concreting. And this is the upper floor. As we go up, the cantilever keep increasing. This is around maximum of 6 meters, the overall of 10 meters around. As we go up, at the topmost, it reaches as high as 20 meters. The floor plan at a higher level, and this is the butterfly roof structure, again radiating centrally from the RC core. So we have got a radial trusses and circumferential trusses, and for planar stability we have got abrasons. And how the sections looks like, the vertical section has already shown. Here basically the hinges is been introduced, as it can be seen in this photograph. So we want to transfer only the moments, no additional forces. So the reason is the connection of concrete to steel is not quite standardized because it goes into the slab, it's not going into the column. So these are atypical connections which generally don't exist in the codes. So we need to develop the details. So because of which we ensure that we make the force transfer system as trivial as possible, because of which we introduce the hinges. So which can be seen at every floors and at the bottom here as well, column. So we transfer only the shears and axial forces. This is the another same section, only thing additionally the roof spine is shown. And this is the overall layout. The horizontal section is taken. This balanced on either side, it can be seen. Both are equally cantilevered on either side from the central portion. And The top butterfly roof structure again supported from the floors. So this being huge cantilevers, it goes as high as around 20 meters from the central core. So we need a higher depth for that case. So we have taken a support from the central location to increase the stiffness. And this is the overall structural system what has been adopted as it, and this resting on the pile foundations, which is of RCC, and stem again RCC. The complete bowl structure comes under steel and composite. And the important thing in this is to estimate the wind loads. Apart from other loads, what we consider, the dead, imposed, and seismic, which are quite trivial in all the cases, but here the most important is being a wind loads, because there is the structure being slender, the dynamic effect, that is slenderness, will come into play, because of which we need to do this. So we have done a wind tunnel study to estimate the wind loads. So the wind loads for the structural wind study and cladding wind study, which is being carried out to estimate the loads. And additionally, the performance estimation, which is the floor vibration study and the human comfort at that level, because the being wind speed quite high, generally we can see that the wind speed at that level is very close to 60 kilometers per hour on an average during service stage itself. Okay, apart from what code says, for which that is around 50 meters per second, for which we need to design for, which is works out to be 180 kilometers per hour, the highest wind speed. But the service wind speed itself comes to be around 60 kilometers per hour. It's also very close to the shore. It's hardly around 5 to 6 kilometers away from the shore. So there will be a continuous wind speed. So the importance is to estimate the human comfort. That's the reason we have carried out this. Now, analytical modeling. So this kind of complicated structures, how the technology has enabled us to really perform these kind of complicated connections. So the analytical tools which enabled us to do this is, the summary of this is like this. From concept sketches, we go for analysis. The global model, that is the complete model being analyzed. In that, again, we do two types of analysis. One is linear elastic, another one is nonlinear. It is to estimate the P delta effects, that is the additional moments which is coming due to the lateral deflection. And we go for a component modeling, because not all the elements can be designed from the global model, and we need to go for a component, that is local models to do this. So in that, again, we carry out number of analysis, that is linear analysis, nonlinear analysis, and we carry out to estimate, which subsequently I will show it how we have done it. So analytical modeling, global model, actually we carried out as a whole with ETAPS. So this complete model is being done to arrive at the stem and foundation system. Again, we carry out this P delta analysis to arrive at the additional forces, because for this kind of tall structures, the deflections are very high. So because of which you need to account this. And we carry out additional verification at the next system, because this being cantilevered out by 20 meters, there will be a lot of wind forces acting in the front. So because of which we need to carry out this. Then next is component modeling. Basically, it is done for the transfer system at 90 meter level. So this being steel being embedded in the concrete, so the systems don't readily subject to a standard designs. So we need to carry out additional analysis. So first in this series is to do the solid modeling. So before we go for this, we take a initial girder, complete the engineering, then go for a single embedment, carry out this, then go further this to arrive at the interaction between the girders. So this we carry out based on the linear elastic, and this is how it is. This is the single girder separately modeled and how it looks like in reality. And this is the bigger picture of the same. So we have got the girders top and bottom. There are flange blades which goes as high as 90 thick plates, and web goes up to 45 thick plates. And at the end, there is an end plate where we have got a horizontal reinforcement, which can be seen in the subsequent slides, which will be actually these are the couplers. Later stage it will be threaded to this. Because of the transportation requirements, we have modularized this. So these steels are of E350 grade, and this plate is going up to 100 to 120 thick plates. So these are all being in plane tension is there, we have gone for a Z35 grade steels. So which is now the technology makes us available these kind of steels, we could go for such a simpler system. Otherwise, the connection detail will become little bigger and leading to a more thickness in the slab. So in the same component modeling, we have carried out a nonlinear analysis. The basic requirement for doing this is to ensure that the failure is being captured appropriately and optimize the system. So linear elastic don't by itself gives such kind of failure philosophies. So we need to go for these kind of models where we model the reinforcements and try to see that how the reinforcements is yields and try to optimize the reinforcements. And next is the butterfly roof structure. Again, we do independent modeling, and the reason being this being done independent model is, again, the overall model takes a lot of time to run and arrive at the final solution. So we can easily carry out this kind of component models and arrive at a solution quite faster. So next, another one is this. The Pinnacle is as high as 20 meters at a level of 112 meters above the tower. Again, this is a completely a steel structure. It can be seen from here. This goes up to this. So this portion is made up of a skeletal structure cladded with ACP, and top is completely a box sections. So the primary difference is being comparing to skeletal, the box section gives more stiffness both from structural and torsional capabilities, because of which we have gone for this box sections comparing to the skeletal system. Now the construction foundation systems is again the pile foundations around 86 piles, and this is around 3 meter thick pile raft. This is the construction photographs. This is the bottom layer reinforcement being placed, the top level reinforcements, and post concreting, this is how it looks like with the RC doubles being left. And these are all the vertical wall constructions, how it progresses and reaches 91 meter height. Now the bowel constructions, though this is the main area where the steel application is being taken. So here the 91 meter level, we have got all the steel girders, which is around 1.6 to 1.5 to 1.6 meter deep girders. Around 14 such girders are there. So in order to erect the girders, we need a platform. So we have created a platform here. So here it can be seen, these are all the radial trusses, as it can be seen from this. Suppose that we place the bottom shuttering, so which can be seen. The actually mock-up is carried out at the bottom because we need to arrive at the appropriate geometry, because which can be trial based. We can't do it at that level, we do it at the base and then take it to the top. So this is how the erection is being done for the enabling works, and after reaching here, we go for a bottom reinforcement. So meanwhile, we need to place the girders, so how the fabrication and erection is being carried out. So it starts with the plate cutting. So all the girders is made up of plates, there is no standard sections. So, and the final girders, how it looks like, and erection sequence. All these things being carried out only with the tower cranes, no mobile cranes being used except for the ground handling. So this is the next girder, how it goes, and it goes into place. And here it can be seen what goes into the concrete is not painted, because to have a better adherence with the concrete. And what is outside, the corrosion protection is being carried out. And it can be seen, this is the reinforcement, which is again lateral connected to the girder. So there are, in the web, there are some puncturing being done to take the reinforcements all around to give the confinement. And this post completion of the reinforcement and concreting. So this accounts for almost 380 cubic meters of concrete continuously done for 21 hours to complete the task. So the next stage arrives having done that. So next stage is to erect this particular beam. So this beam is not erected separately. This comes with the L shape, so that post erection it's connected these two locations together. So actually this has been done away from here. That's around 350 kilometers from here, and then it's complete set comes to the site and only the erection takes place. So this being a longer piece, so one splice was done here at the middle of the column, so which is assembled at the site and then taken to the top. So which can be seen here. After erection, the typical connection how it looks like with a single pin. Similarly, the same pin appears at the bottom as well, floor level. So this post erection of the secondary beams, and this is the metal deck with the shear studs with the skin reinforcement for the deck, and post concreting how it looks like, and this after all the floors being concreted. So post that actually we erect the enabling steel work for erecting the facade. So this it can be seen here. So after erecting, we have got around 18 of such trusses. So after erection of this, we go for a placement of the facade panels. So which can be seen from the top that 18 trusses all around it is being placed. So only after removal of this, we can go for a roof truss erection, which can be seen here. So once it is removed after erection of facade panels, we go for a erection of the steel trusses. So this is after completion of the erection of the roof trusses and purlins to receive the roof sheeting work. This is roof sheeting in progress. This is only the single layer is been erected. The second layer is under progress now. So this is the erection of the Pinnacle, how it goes. All being done with the tower crane. And this is the facade glazing. Actually, we have got a facade panoramic in the front of the panoramic lift and bowel and at the roof spine. So we have got a separate steel torsion beam all around the structure at the floor levels. Here it can be seen over which the steel mullions supports this. The primary reason we go for steel mullions is one is the larger span, it goes as high as 7 meters at the bottommost, because this is quite steep at the bottom. As it goes up, the slope keep reducing. So the wind pressure is being quite high at that level and leads to a pressure of around 6 kPa. So with the aluminum mullions, it's quite difficult to sustain the load, so we need to go for a steel mullions. So this is the steel truss, what was shown previously, used for erecting the facade panels. So as we complete facade panels, we keep removing it and go ahead with the erection of the roof truss. How it looks like from the center, actually there are some staging elements which is being placed because the roof fireproofing work are under progress. And the important component of this system is building maintenance, the post-construction, how we maintain the total structure. So we need to have for each of the facade elements and roof structure out the maintenance and safety systems. So one is bowl glazing. So we use the upsealing systems as well as for the panoramic lift in the front. And Pinnacle, we go for a regular ladder with a safety protection, and butterfly loop, we have got a safety follower system. So the hooks being placed like this, so it's actually basically called a Spider-Man system. So the person starts from top, keep cleaning and comes down. Again, you need to go to the top to go for another line of cleaning. So how it looks like here. So this is the safety pins, can be seen here. So this is the partial completed view of the building, and this is the intent and how we achieved the final